Chapter 11 Kinetic Theory of Gases, Section 11.3 Collisions and Pressure. Pressure results from the collisions between the gas particles with the surface areas inside a container. We will be able to derive PV equals nRT for ideal gases, assuming all collisions are elastic. We will look at the motions of one individual gas particle and then extend it to all gas particles inside the container. And you can see over here all those particles are colliding with the surfaces. During the collision, the momentum of the colliding particle changes, and that change is due to the force exerted by the surface area and the particle. And force divided by the area is pressure. So now let's do the derivation. Let's study N mole argon atoms in a box. Let's say the side length of the box is L. Alright, over here in the x direction. And this box has a bottom area of A. So the volume is A times L. Now we'll just look at one particle, and we will look at the motion of this particle in the x direction. We know the average kinetic energy of each atom in each dimension is 1/2 kBt. This is from the previous section. In the previous section, we derived the root mean squared speed, which is the square root of 3 kBt over m. Therefore, the average kinetic energy of the particles is 1/2 of the average of mv squared, and this is equal to 3/2 kBt. So really you just need to square this. Alright, you square it, you get this, multiply by m. Alright, multiply by m, and then divided by 2, you get 3/2 kBt. And that's the average kinetic energy of the gas particles. Now we're going to assume the x dimension, y dimension, and z dimension have the same distribution of the speed. And then we have this in each dimension. The average kinetic energy is 1/2 kBt. In 3 dimensions, we have 3/2 kBt. 1 dimension, just 1/2 kBt. And now we're going to just look at the collision between this single particle and this shaded area, A1 area, and see if we can derive the expression of pressure. And eventually we will get pressure equals nRT over volume for the ideal gas. Within delta t, time period delta t, an argon atom can travel first to right as indicated by this arrow and collide with the shaded area, change its direction, collide with the A2 area, change its direction, get back to the original position, and keep doing the traveling. How many times? Well, this particle will have to travel a total distance of 2L to return to its original position. So let's look at this. We're going to move this particle to this area, change its direction, change the direction again after another collision, and get back. So you just need to sum up the length of the first black arrow, this arrow, and this longer arrow, and this arrow. Overall, this is L and this is L. Therefore, this particle will need to travel a distance of 2L to return to its original position. I'm going to call this a travel of 2L as just one collision cycle, because during this one collision cycle, this particle collides with A1 once, it collides with A2 once. But now let's just focus on this shaded area A1. So this particle moves in this direction and bounces back. And then how many collisions take place within this time period? Well, again, we know this particle needs to travel a distance of 2L to have one collision with this A1. So really, if we know the total distance this particle travels divided by 2L, that would be the number of collision cycles and also the number of collisions between the particle and the A1 shaded area. Therefore, the number of collisions between this atom or this molecule or gas particle and the shaded area within time delta t is the distance it travels within delta t, which is Vx times delta t divided by 2L. So that's the analysis. The number of collisions within delta t between the particle and A1 area. Well, you may wonder, this particle might also moving in the y direction and also z direction. That's true. It's just we do not care about the motion of the particle in the y direction or z direction. We're just focused on the x direction. Even if this particle moves in the y or z directions, it does not change our analysis here for the number of collisions between the particle and the A1 area within time delta t. Now each collision between this atom and this surface area results in a momentum change of this particle. It's just because we assume the collision is elastic. So before the collision, the speed is Vx. After the collision, the speed is also Vx. However, the velocity changes. It goes from positive Vx to negative Vx. Or if you define the direction in the opposite way, it changes from negative Vx to positive Vx. So the magnitude of the change of the momentum should be 2 mvx. It goes from negative mvx to positive mvx, or from positive mvx to negative mvx. Either way, the magnitude of the change is 2 mvx. Now we have this number of collisions. Alright, for each collision there's this much momentum change. So we're going to multiply these two together. That's going to be the total momentum change caused by this A1 surface area to this particle within a time period of delta t. Now let's look at this equation. 2 and 2 cancel. Vx times Vx. We have mvx squared on top, delta t on top, L on the bottom. Again, within delta t, the total momentum change of one particle is this. But what if we have MO particles? When we have MO particles, we have n times Avogadro atoms or molecules or particles. So we have to kind of sum up all this for all particles. It's going to be the sum of mv squared delta t over L. This I is the index for the atoms in the gas phase, or the particles in the gas phase. I is from 1 to n times Avogadro constant. So again, this is just the total momentum change of all gas particles caused by the collisions between the particles and this A1 area, shaded area. Again, the total momentum change caused by the A1 surface and the particles within time delta t is this much. Over here we have the sum over all particles. Alright, and we can clean it up because m, delta t, and L do not depend on I. So I'm taking those out. Now we have just the sum of v squared for all the particles. Well, remember, the sum of many data is just the number of data multiplied by the average. Right? This is the sum, this is the average, and this is the number of data. So that's why we got this here. Since the root mean squared speed is the square root of 3 kbt over m, we have this equation by having the left side squared and the right hand side squared. In each of the 3 dimensions, we have vx squared equals vy squared equals vz squared, which is just 1/3 of this, which is just kbt over m. The total momentum change over here between the particles and the A1 shaded area is thus over here. I was replacing mv squared with kbt. And note here, the Avogadro constant times the Boltzmann constant is equal to r, the ideal gas constant. So we have this simple equation. That's the total momentum change of all gas particles caused by the collisions between these particles and the A1 shaded area. And Newton's law tells us we can't just change the momentum of the particles without any force. We need a force, and we need a period when this force exerted to those particles. So this momentum change is due to the force during this time period. So now you can see we have delta t on the left and right sides. Both sides divided by delta t, we have nRT equals FL. This allows us to determine the pressure, because force is pressure times the area. And now we have nRT equals P times the surface area of A1, the shaded area, times the length of the box. A times L is the volume of the container. Now we have PV equals nRT. In the above derivation of PV equals nRT, we assume that there is no attraction or repulsion between the gas particles. Therefore, the momentum change of the particles are caused only by the collisions with the surface of the container. But what if there is attraction or repulsion? The attraction between the gas particles reduces the momentum change of the particles in collisions with the container surfaces, and therefore lower the amount of force and lower the amount of pressure. Well, this is also how seatbelt works in a car accident. In a car accident, well, the driver is likely to hit the windshield. But what if you have the seatbelt pulling the driver away from the windshield? It's almost like attraction pointing towards the center of the car, away from the windshield. And now, even when a collision between the driver and the windshield transpires, the severity of the collision is reduced by the pull from the safety belt. Similarly, when a particle is about to collide with a surface, if all other gas particles are attracting the colliding particle, it's going to reduce the magnitude of this collision and lower the pressure. On the other hand, repulsion between the gas particles increases the momentum change in the collisions with the container surfaces and then elevates the pressure. Let's use the car accident as another example. Repulsion is almost like someone pushing you from behind when you are about to hit the windshield. And if there's no attraction between the gas particles, let's just focus on this repulsion. That means you're not wearing the seatbelt, no attraction towards the center of the car, only repulsion that pushing you from behind toward the windshield. And that push or repulsion would increase the pressure between you and the windshield. That will increase the severity of the collision. You will have higher pressure. In summary, attraction between the gas particles reduces pressure, the repulsion between gas particles increases the pressure. And we can quantify this statement in the Van der Waals equation. P is RT over molar volume minus B minus A over molar volume squared. So when A is larger, you have more attraction, P is smaller. When B is larger, well, you have more repulsion. P is larger. So again, when A increases, P decreases. When B increases, P increases. Attraction reduces pressure. Repulsion increases pressure. And this statement is quantified in this Van der Waals equation. What if A is 0, B is 0? Well, then you have the ideal gas equation. In the Van der Waals equation, B is also a measure of the size of the gas particles. The larger the size of the particles, the larger the value of B. In the ideal gas equation, we are assuming the size is just 0. But what if we're looking at real gas particles with a finite size? In that case, the collisional frequency is higher than the ideal gas just because the traveling distance between two successive collisions would be less than 2L. So very often you do not have to travel the whole 2L distance to get back to the original position. It's because the particle may collide to the surface, change its direction, but not all the way to the opposite surface. Maybe over here, it collides with another particle and changes its direction immediately. And that means the particle can just hit here and then hit to another gas atom and change its direction and get to its original position without traveling the whole distance of 2L. That means you have a higher collisional frequency, and that means you have a greater force on the surface area and a higher pressure. Finally, something trivial. In the derivation of PV equals RT, we assume there's no gravity. But if we consider the gravity, then the up motion of the particles should be slightly slower than the down motion, right? Due to the gravity. And therefore, the momentum change caused by the collisions with the top surface is smaller than the momentum change caused by the collision with the bottom surface. Alright, so if a particle is moving up, right before the collision, I think its speed is pretty small. It's smaller than average, and when it collides to the bottom, the momentum is probably greater than average, all due to gravity. And because of that, the air pressure on top of the Mount Everest is lower than the pressure at sea level.